How's it going? In this video, we are going to have a look at compiling GLSL code into SPIR-V code and loading that in at runtime. So in the past, it was very common for me to use a batch file to run GLSC. I think that was the one, GL Shader Language Compiler, to compile my GLSL into SPIR-V code. And then in a previous video, I just provided the SPIR-V files and said, these are the files, we'll work with them. But it's a little bit cringe. And the issue with that is that by and large, the biggest error I ran into was editing my shader code and then forgetting to run the batch file. And it's just a little bit annoying. So what we'll be doing today is we will be using shader-C to basically do runtime compilation. So I'll just minimize this and we'll see the various stages. So these are the stages we're going to run through. First of all, we'll ingest some GLSL and we'll pre-process that code. I don't think this is going to do anything, but it was in the standard example, so I'm going to include that. And then we're going to take that pre-processed code and we're going to compile that into SPIR-V assembly code. And then we are going to compile or assemble that assembly code into a SPIR-V binary file. Okay, so one step at a time. To start with, I'm going to need shader-RC. So if I go to my local disk and my Vulkan SDK, in here there's a bunch of things. Just go to libraries, and under shader-C we got a whole bunch of these libraries, but two of them are really important. There's shader-C combined and shader-C combined D. Now the difference between these is the configuration that we're running under. So the D stands for debug. I'm running in debug mode, so I'm going to grab the combined D. I know it's quite big, but I'll grab it. And I will just put that in my dependencies folder in the lib folder. Then I'll go back to my SDK and I'll look in include and I'll grab the shader-RC folder, bring that back, and I'll put that in my dependencies folder so I have access to that header. Excellent. So if I were to save this right now, well, actually I can just type it in now. So I'll go shader-RC, shader-C.hpp, and fingers crossed, come on, come on. Well, anyway, it should include it. Now, what I'll do as well is I'll go to my properties, linker, input, and here's where I specify all the library folders that I'm going to include, and you can see here I've got shader-C combined D lib folder file. Cool, so we are instructing the program that we want to include that. Okay, so I'll leave that for now. I don't know why that's not. There we go, just quickly reloaded, just Visual Studio being Visual Studio. So what I'm going to do is for a bunch of these stages, they are pretty much going to have identical inputs. So I've made this struct. It's a general struct representing all the stuff, all the info which is needed to compile. So we have the file name because all of these compilation functions are going to take in the file name and they'll use that for error messaging. So if we go to compile one of these stages and it fails, it'll print out an error, but it will also indicate which file caused that error. We're also going to have the type of shader that we're compiling. We're going to have a buffer of all the characters indicating the source code which is going to be compiled. And then we're also going to have the options for the compiler. So let's go to the pre-process stage. I'm going to sort of take it one step at a time. So this will take in GLSL code. It will pre-process that GLSL code and produce possibly changed GLSL code. So for my setup, I'm going to grab my logger object. And I'm also going to have this compiler object, and this will actually be the same for the setup on the other functions as well. So I'll go ahead, put that in. Okay, now for compilation, I'm going to run a preprocess function, and this is how it goes. I'm going to return a, here we go, preprocessed source compilation result. That's a bit of a mouthful there. And the way I'll do this is through my compiler object. So I'll take my compiler and I'll say, okay, well, this is all we have, right? Preprocess GLSL. This is going to take a few things. We're going to need to take the source. No, actually, I'm not going to use that version. I'm going to use this version here because I'm not working with a string for my source text. I'm working with a vector of characters. No problem at all. So I'll go take my input. Sorry, not input, info. Then I'll also pass in my info, so the number of bytes to read. And then I'm going to need the file name, which again, I've got this, no problem. I'll look at my info struct and here we go, file name. Then we're going to need the compilation options. And again, this will pretty much be the same set of options for all compilation operations. So we'll grab that, options. Whoops, I missed one, and that is the type of thing that we're compiling. So that's info, just like that. Awesome. Okay, so we've done this operation. We're then potentially going to have an error, so we can check for that. So we can get that result object. We can say, hey, get compilation status. Check if that's a success, and if it's not, whoops, then we can go ahead and print out the error message. So we can say, hey, go result get error message, print that out. Okay, so what we're then going to do is I want to get the result. And what this will be doing is it will be basically storing a string inside the result object, which has all of the transpiled, all the compiled, pre-processed GLSL code. So I want to take the contents of that string. We can think of it like a string. It's just a beginning and an end. It's a contiguous block of bytes. I want to copy that into somewhere. And it turns out this is really useful because we've got a string of info, of source code, and this struct has a bunch of characters, which is the source code that was going to be input to the compiler. So a little dodgy maybe, but I'm going to basically mem copy from the result back into the compilation info struct so that then I can use that for a further operation. So what I'll do is I'll just grab a pointer to the beginning of that chunk, and the way I do that is I go result C begin. As we can see here, it says returns a random access contiguous iterator pointing to the start of the compilation output. Okay, and then I want to know how many bytes to copy. So I'll have this new size variable, and that will pretty much be the offset. So we'll go the result end minus the memory location of the beginning, and that will be the number of bytes to copy over. Then we can go ahead and resize the buffer that's going to hold our output, and then mem copy into that. So we'll go mem copy. Why can I not type? So the destination that we're copying to will be the source. We'll get its destination with the data function, and then we're going to be copying from the beginning of the result, and the number of bytes we'll be copying over. I'm nervous. It's been a while since I've done one of these things. Okay, cool. So we've got that. Then, really helpful for debugging, sort of, is, and just for fun, is I'm going to print out the result. So I'll just do a bunch of printing functions here. Okay, so I'll just sort of indicate the stage that we're on, and I will fetch the output of that compilation and store it into a string. So I'll make a string, and I'll initialize it with this memory chunk, the beginning of the memory, and then the end of the memory. Then I'll go ahead and I'll log that with my logger. So there we have it. A lot of the other stages will use this same basic pattern, so I'll be using a bit of copy paste here, but I'll try to work through how this is going. So I've got my shaders folder, and inside I've got shader.frag and shader.vert. When it comes over here to making the shader objects, I've shortened this a little bit. I'm just going to pass in the name shader because I'm going to have the understanding that all the shaders will be in the shader folder, and the extensions to those files are right there. We know they're vert and frag. So then we go to the shader code right down here. Okay, so we've got this name, and I can see there's a few errors here at the moment, so I'll just put this in for now. Just to sort of clear those errors out. I'll populate that in a second. But what I want to do is I want to get this running a little bit. So I'm going to use a string stream to build this file name. What I'll do is I'll take that file name, I'll give it the folder, and then the name of the shader, and then the extension, which in this case is vertex. I'm also going to have a string which will hold the actual file name, and I can initialize that using the file name builder's string function. After doing that, I can clear off the file name builder and use that later on for something else. But anyway, so in order to kick off the first compilation stage, I'll need to populate some compilation info, starting with the file name, which will be given by the file name there. Then what else do we have? Kind shader C vertex shader. Awesome. This is all defined in the header. Options, source. Yeah, let's do the source code. So previously I had the read file function, and what that did is it basically took in the file name and then it gave back a vector of characters. So I can go ahead and use that. That should be fine. And then I will put that in and just see what happens. Oh, whoops, my bad. It's already been defined up above. Okay. Stop talking to myself. That is fine. There we go, to stop it from squawking at me. Okay, right, so we're getting an error, but that's totally fine. Just building it up one step at a time. So far, so good. So we've gone through, we've read that vertex shader, and this is pretty much just, this is the code after pre-processing, which there's no difference. It's the original code, but at least it's reading the file correctly. So I'll get this out of the way, and we'll get on to the next part, which is, yeah, compiling that into SPIR-V assembly code. So like I said, a lot of this is going to be the same. This stuff is all the same. As a matter of fact, I'll grab all of it and copy it over. Okay, this stuff is fine. Go compile GLSW to SPIR-V. But this is going to return a SPIR-V compilation result. So grab that. Okay, but everything else is the same. It's the same stuff. It takes the same info. So again, we check our compilation status. We could have an error, could not. And then down here, what do we have? Oh, why does that not work? My bad. I'm skipping a few steps. So we have compile GLSL to SPIR-V assembly. And this will return an assembly compilation result. This is a lot of fun. But side note, I ran into a lot of errors while I was going through this process, and I found it very hard to find info about that online. So that either means this is a problem which isn't worth solving, or that this is very useful stepping through this. But anyway, so we go through, we compile that GLSL to SPIR-V assembly. There we go. We log out an error if there is one. We then copy that whole character buffer onto our source vector in our info bundle, and we're also going to print everything out. So this is the SPIR-V assembly code. Okay, I think that's fine. Let's go ahead and do that. So we've pre-processed, now we'll go, so again, the same error, that's totally fine. Let's look at the output. So here we've got our GLSL code, that's fine. And then down here we're setting up our SPIR-V assembly code. Totally fine. Yep, this is assembly code. It's pretty cool to see this actually. I think that's very cool. And down here it's just complaining and it's saying, hey, you haven't done everything. You haven't done everything, and that's totally fine. So we'll get this out of the way and we'll keep going on. Okay, so we've compiled to assembly, and then the next step is we need to take that assembly code and compile that into an actual SPIR-V binary file. So what I'm going to do here is I'm going to take assemble to SPIR-V. We can hover over here. It says nothing. I'll just get this out of the way. Okay, there we are. So assemble to SPIR-V. It says here, you know, assembles a given SPIR-V assembly and returns a SPIR-V binary module. Okay, so we can look through the options here. This is the string version. We also have another one where we can put in some options, and then we have on and on and on. This is probably the one I want. I want a pointer to the data. I want the number of bytes that I'm passing in and the options. So I can go ahead and do this. And it says here that will return a SPIR-V compilation result. So pass in the pointer, the data size. Okay, so things are a little different here because what we've been doing so far is we've been compiling and then we've been taking byte buffers, basically like, you know, binary buffers. But this assemble to SPIR-V will actually return a contiguous chunk of uint32s. Basically, it's 32-bit words. As a matter of fact, we can see here that if we go to cbegin, that will return a pointer to a uint32. Now, what we could do is we could still read this as a whole bunch of bytes, but I found there was an issue with endianness, or just it wasn't working. So what I'll do, yeah, has to be const. There we go. This is fine. And at this point, I'm going to actually put this into a vector. And just to make this a little more meaningful, instead of new size, I'm going to call this word count. And I'll mem copy into that. So we have word count, and every word is 32 bits. So we'll take that into account. Cool. Okay. So in theory, output should now have. And there's something we can do to, let me just go binary. There's something we can do to actually verify that this has been read correctly. If I bring this up, just looking over here at the SPIR-V specification, number 2.3. So we have this file, and this file has a bunch of 32-bit words, as we can see here. Word is 32 bits. And the first few words have specific stuff. Specifically, this first one holds what's called a magic number. Here it is. That's the number. And it's used in order to determine the endianness of the system. So we should be able to load this file in, look at the first 32 bits, and then adjust the endianness so that the magic number appears, and this is an indicator of the endianness of the entire file. Yeah, there we go. I've loaded that in ahead of time. So sort of 11.7. There we go. That's sort of the thing to target. So what I'm going to do is I'm actually going to take the magic number and print it out and verify that it's correct. There we go. So we're just reading off the first word, checking it basically. Yeah, so I'll go down and do this. We'll have compile file, give that a go and see what happens. Okay, so we've got an error. Okay, so as you can see, we have got the correct magic number, but we've got some sort of error. Now, interestingly, the error is not where I thought it would be. And the reason for that is that I'm not actually checking for this error properly. So, oh yeah, oh my goodness. Okay, just give me 1 second. What I'm going to do for now is I'm just going to pretend that this is working, and then I'll modify it a little bit. We'll see what happens. But I'm going to go and basically do the same thing for the fragment shader. Okay, let's have a look. Oh, wow. Okay, it works. Okay, so that's fine. That looks good. I will modify this a little bit. So as we can see, we basically got the same thing as before, but it's not necessarily, like, it's easier to change on the fly. So I can go in, for instance, to my vertex, and let's say that I want to make one of these points. Like the red point becomes, what is that? Yellow? I don't know. Let's find out. So we compile. Yeah, that red point is yellow, and I didn't need to run a batch script in order to recompile. I just changed the text, and there we have it. It's pretty good. I'm pretty happy with that. Now let's modify this a little bit, because remember that up in here, where are we? We've got this options field, but otherwise we haven't we haven't done anything with options. So let's play around with that. One thing we can do is we can enable some optimization. There we go, set optimization level. And let's say, well, let me have a look at this. So we've taken a shader C optimization level. So we'll go shader C. There's a few options here. Optimize for performance, size, or don't optimize at all. I'm going to optimize for performance and see what happens here. Here we go. Okay, so it's handled it just fine. I am going to modify things a little bit. So again, go in here, go info, options, set, what do we have? Let's set target environment. Let's set the OpenGL version, for instance. I'll set the set the Vulkan version as well. Let's see what happens. I'm trying to make it error out, but we'll see. Okay, so I sort of breezed past this, but originally when I compiled this, we had this in version 1.0 SPIR-V, but now that I've specified that we're using Vulkan version 1.3, it's using version 1.6 SPIR-V. And the assembly code seems significantly smaller, just from looking at this. Or maybe it's a different thing. I'm looking at a different, I'm rambling. I'm rambling, which means we are at the end. That is it. So, again, there you go. Today what we were looking at was runtime compilation of GLSL into SPIR-V, which makes things pretty nice. I'm not playing around with like hot reloading shaders or anything like that. It's never really been my thing, but we could do it. And as you can see, we are still getting a bunch of errors. And the reason for those errors is that everything is hard-coded without any synchronization. So in the next video, there's a good chance we'll be looking at synchronizing this stuff. Synchronizing our draw operations. But yeah, that will be it for now. Thank you for watching. Hope you had fun. And I will see you again soon. Bye.